Is the abbreviation for OPAMP?
Operational amplifier.
Yeah, it's operational amplifier. Thank you. So we're going to deal with the operational amplifier as the next topic. So we'll be learning about what is an OPAMP, what are the characteristics of an ideal OPAMP, what is common OPAMP circuits, and some applications and references. So this would be the outline of today's class. So what is an OPAMP? As Joel told, it's an operational amplifier, okay? And it is a device used to amplify a signal using external power source. Okay? And it is a transistor. Basically, op-amp is a transistor which is made up of many transistors, resistors, and capacitors. Okay? This is the composition of an op-amp. It consists of all these elements put together. Uh, they make an op-amp. Can you tell one op-amp number, operational amplifier?
LT 1115.
LT 1115. Any other numbers? Any other op-amps? Operational amplifiers number? 741. Yeah, that's a very famous op-amp. Yeah, these are some of the operational amplifiers we have in the market, right? Now, my question is, why do you need an operational amplifier? Why do you need an operational amplifier? Francis,
Yes, sir.
why do you need an operational amplifier, Francis?
So it acts as a differentiator, integrator.
Joel, when I ask you, you can tell. Francis,
Sir, for amplifying, sir. That's
amplifying amplifier is there, right?
yes,
Why do
sir.
you need an operational amplifier?
Sir, for increasing the performance.
For increasing
Performance.
what?
Efficiency, I like that.
Efficiency. Okay. Joel, you said something. Operational amplifier is what?
Differentiator, integrator. It is for a specific application, sir. It is
For
designed.
inverting and non-inverting one.
Pardon? Strike?
For inverting and non-inverting.
Non-inverting. You said it's a multi-purpose device. Okay. Right. It's basically used for performing various logical operations. That was the main reason why they went in for the op-amp. Okay. Something like what Joel told. Many operations can be designed, like differentiator, integrator, summator, and other applications. Okay. That was and why did they go for op-amp is the performance was very good. Okay, as Francis told, the performance metrics for an operational amplifier is very good compared to a normal analog circuit. Analog amplifiers, operational amplifiers almost gave close to 95 to 96 percentage performance. That's something phenomenally big. Now, when you look at the brief history of uh, the op-amp, it started from the vacuum tubes. Okay? Way back in 1946, the operational vacuum tubes operational amplifiers was designed, and then it went into the commercializations. The first commercial op-amp was available in 1953. Okay? Then we had discrete op-amps coming into existence with 1961. Then we went on for uh, the monolithic op-amps. Okay, and still now we have a lot of op-amps coming into play. But the era started with what we have today with monolithic op-amps on on from 1965 onwards. Okay? It's a long history, but it took its own traditional changes. And why they are still sticking on to this particular device is because of its performance. It's impeccable, and it has got so much performance metrics that default every designer goes for it. Right. So the most conventional one is the right old, that is 741. All of you know this op-amp. You should have definitely studied a paper called Linear Integrated Circuits, in which you should have studied one full paper on it on 741. And this is the pin configuration of 741, which was invented by Fairchild. Okay, and this is the configuration of an op-amp, the modern IC, which consists of 8 pins. The first one is offset. Then we have two input terminals. The two input terminals are inverting terminal and non-inverting terminal. Then you have the power supply, positive and negative swing. Output comes across 7. Then there is an offset null. Then there is a NC pin, which is non-conducted pin. Okay. This is the configuration of a 741 op-amp. Now let's look at how does the operation of this amplifier, a traditional op-amp, looks like. Okay. This is the symbol of an op-amp. Okay. So the op-amp has got the most significant feature of having two inputs. Okay, like we have studied already a device with two input. What is that? We have already designed one device with two input. What is that? Come on, guys. We have device. We have studied a device with two inputs. Yeah, that's right. Diff amp, right? But it had two outputs. Okay. Instead of that, we have only one output over here. Okay. So this is diff amp. Change from diff amp. You have two inputs. One is positive terminal. The positive terminal is called as the non-inverting terminal. Okay. And negative terminal is called as the inverting terminal. And this V out is the output terminal. Okay. Then you have two supply, both positive and negative supply voltage given. Okay. So operational amplifier is basically a differentiator. Okay, with a K factor, with a gain factor K. So this output expression V out is given by K into uh, V plus minus V minus. Okay. So this is the basic standard equation for an operational amplifier. All of you know it. So with this, we will go into the characteristics. Okay. Now you have the swing from V plus to V minus. Okay, V plus to V minus, and the gain is given by the slope of this particular curve. The K value is given by the slope. Okay, slope of this gives the uh, output. Okay, this is for. Can you tell what is this output for? This characteristics, that is V in V out minus V in characteristics, is for which amplifier? You have two inputs here. One is inverting, the other one is non-inverting. Now, this graph is for which one? All of you have studied it. Ahatyan?
Yeah.
Yeah, Ahatyan, we were talking about two terminals. One is inverting, the other one is non-inverting. Now,
Yes, yes.
what is this characteristics meant for? Adyan,
Sir.
you should have studied LIC.
Yes, sir.
What is this characteristics? This is for only two options, man. Is it inverting or non-inverting?
Maybe non-writing, sir.
It is non-inverting. Yeah. If it is for inverting, then the graph will change to what?
Maybe K value will be at
Yeah,
minus.
the A value should be negative. So your
Yes,
graph will be something like this.
yes, sir.
My sticky pen is moving very badly. Yeah, it will be like this. Okay, so your slope A value will be negative. Okay, so that is the two things you have to keep it in your mind. Okay, for positive, this is the K value. If it's an inverted terminal, then it should be the other way down. Okay, so this is another characteristics you should keep it in your mind. Now, let's look at what are the characteristics for an ideal op-amp and a real-time op-amp. Okay. Now, these are certain characteristics which you already know. One is the voltage gain. Okay, voltage gain. What is gain? Like class, who was it? Akshaya was telling it is V out by V in, right? The value of the ideal op-amp should be infinite. Okay, then the second parameter, this also we have learned. What is the input impedance? Input impedance should be infinity. Okay, and then the output impedance should be zero. Okay, this also we have learned. Then bandwidth, we saw how to estimate the bandwidth for a feedback amplifier. So for an ideal op amp, the bandwidth should be close to infinity. And then the last one, this is offset part. Uh, Offset comes into designing the exact value of fluctuation. Okay, so that should be zero. Your input offset voltage should be zero. So these are the five major characteristics for an ideal op amp. Okay, so keep this in your mind because we will be using it for practical work, real time. Now, if I split it into real time, ideal, and real time, you know what is it, ideal and what is real time. When you're talking about ideal, this is the ideal condition. Okay, you see on the left, this is ideal one. Okay, so ideal cases, you will not have any input impedance. So this is the ideal case. Okay, and the parameters we already seen. Gain is infinity, bandwidth product is infinity, resistance is infinity, and your output resistance is zero. Okay. But what happens to the real time? When it comes to the real time, obviously there is a change. You have a change in the input part. Now, what change is there? You have an internal resistance. First thing we keep it infinity, but here we have an internal resistance. Okay, so the internal resistance is given to be Rn. Okay, then about our output resistance, this you know how to draw it for a transistor. So Gm into Vin, and the output resistance should be in series. Okay, because the value should be zero, close to zero. So this is the real-time op amp. Now look at the gain factor. That is awesome. You have a gain of 10 power 9, 10 power 5 to 10 power 9, which I don't think so you'll have it in the best of cascode amplifiers. Only cascode you do it, you might come somewhere close to 10 power 6 or 7. Okay. But this fellow pumps it to 10 power 9, which is the best, right? And also the bandwidth. Look at the bandwidth. It's almost megahertz range you're working. Okay, which is the best. Okay, of what you can have. And then you have the input resistance pretty high. 10 power 12. 10 power 12 is how much, Mr. Yaskum? Yeah, Joel, 10 power 12 is how much?
More,
10
sir.
power 12. Pardon? 10 power 9 is how much? Minus 9 is nano.
That is
Pico. That's right. Yeah.
actually,
10 power is pico, right? And then your output impedance is also pretty much less. It's almost close to 1K, 100 to 1K. So this is the comparison of real-time op-amp and a ideal op-amp.
So
Now we
now,
finished
sir,
two
pico
topics.
means minus, sir. Minus
Minus,
12.
right? Yeah, 10 power 12 is how much? Sorry,
Giga ன்னு நினைக்கிறேன்.
gigawa. 10 power 12 is gigawa. 10 power 12 is what, man? Heard this word tera? Yeah,
Tera, tera.
I think it's tera. Okay. Giga is 10 power 9. Okay. So that's the characteristics. Okay. Now we'll go to the next thing. So we've seen two topics. What is an op amp? We've seen. And then we saw what are the ideal and real time characteristics of an op amp. Now we'll go to the common op amp circuit and we'll try to see the characteristics. So this is the basic op amp. All of you know, right? So the open loop gain is given to be V out equal to K into the difference of the input voltage. Okay. And the value of K is something amazing. Look at the value. What is the value? It's close to 10,000. Okay, so that is phenomenally big. Yes or no? Right. Now, we'll talk in terms of loops. This is open loop, okay, and this is closed loop. All of you know, right? The input is given to the inverting terminal, non-inverting terminal, and the input here is also given to the inverting terminal, and then you have a feedback. So that's how the closed loop condition is. Okay, so this is the open loop and this is the closed loop condition. Is that clear? Thanks. Now, can you write the expression for V out for non-inverting terminal? Can you write the expression for non-inverting terminal? There are two types of inputs you can give. One is for the non-inverting. The other one is can you give the expression for V out for a non-inverting terminal? Let's see how many of you can give. I'll go to Miss Ashika. Bean is equal to, is that right? Ashika?
Yes, sir.
Yes, I think Mr. Isaac has given V in equal to R2 by, what is it? R2 by R1. Yeah, is that right?
Yes, sir.
Okay, let's see. Okay, it is R2 by R1 is minus. It should be yeah 1 plus R2 by R1. Okay. Yeah, I think R1 plus R2. It's inverse. The V out by Vn is going to be 1 plus R2 by R1. Okay. So you can look at the derivation for it. It's a voltage divider bias concept. So uh, that's how we get this expression. V out is equal to 1 plus R2 by R1. Okay. So that's how it is. What is this? Won't come. R2 by R2 plus R1 won't come. Joel? Okay, fine. You end up over here, right? And then for the inverting terminal, yeah, now calculate. I think I've given you the answer also, right? I have given you the answer. There you go. Sorry, okay, no problem. This is an example for a non-inverting amplifier. You have to find out the V out. Calculate. Okay. Yeah, now take out the question. I'll give you the question. Let's see, we calculate out. Find out the V out. Given that Vn is equal to how much? 1 volt.
So for inverting and for non-inverting, sir.
Non-inverting, 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 no inverting. Inverting, you look like that. Take down the question. Uh, Find out the V out of an non-inverting non-inverting amplifier. Given that Vn is equal to 1 volt, R1 is equal to 5k, R R1 equal to 5k, and R2 is equal to how much? 10k.
10K.
Yeah, go ahead. Calculate what is V out. All of
3
you.
volts.
Found the answer. Okay, that's good. Is it okay? What is AF then?
So
What is AF? Gain of the non-inverting amplifier. Find out the AF. Oh, sorry, it's AV, right? Your voltage. Okay. What is the voltage gain?
3, sir. 3, sir. Just a 3
Yeah. V out you found out, right? V out is nothing but
volt.
you should get it 3 volt, right? And if you calculate V out, then AF is how much? AF is how much? AV, sorry. It's 3. 1 plus RF by or R2 by R1, right? So it should be 3. Yes, all of you? Right. We have completed the non-inverting terminal. Now we'll go to the inverting terminal. Okay, inverting terminal of an op-amp, it looks like this, right? So inverting terminal is not changing. Okay, this is the inverting terminal. Look at this. This terminal is the inverting terminal. You have input Vin given, okay, and you have an Rin and Rf. Okay, so this is the feedback element over here. Now, what would be the V out of this? I think that was the thing which Isaac gave first. So it is minus Rf by Rn. Okay, that is for the inverting terminal. Isaac. Okay, you gave the expression for this. So this is minus Rf by Rn. I think we can go through the other analysis later. Okay, now take down the question for inverting amplifier. Determine the output voltage for an inverting amplifier, I think your Vin is 1 volt, RF is 10K, and RI is 5K.
2
We'll
also.
go to Try, I'll tell you. I'll call you that time you tell. We'll go to Mr. Ashwin Raja. Ashwin Raja,
Sir,
what is the AV?
P out by V in.
No. Here it is V out by V in. Okay, V out by V in is equal to what? For an inverting amplifier, V out by V in is equal to what?
Minus R1 by
R2 by R1, right? It should be RF, but oh, my battery is going off. 1 minute. Yeah, minus. Go ahead, Ashwin. Minus
sir, minus R1 by R in plus
R.
R1.
No. Can you come back once again?
Sir, minus R1 by R in, sir.
Look at the circuit. This is RF by RN, right? So your R1 is what I've told you to be 1 volt. How much is it R1? So your RF is 10 and your RN is 5. So what would be your AV? What is your AV?
Sir, minus 2.
Minus
sir.
RF by RN. So how much is the value?
Minus 2, sir. 2.
Pardon? Value?
Sir, 2, sir.
2, right. Now what about the output voltage?
Minus 2, sir. V out.
It is 2 volt,
Hmm.
right? Yes or no?
Yes,
Minus
sir.
2 volt.
Hmm.
Good. So that is the output of a inverting amplifier. Okay, is that clear? Now please look at the input. Okay, the input is a sinusoidal wave, right? And look at the output. The output is similar to that of an amplifier. Okay, I'm sorry, this should be for the inverting, non-inverting output. Okay, the non-inverting output is this. Now, if it's an inverting output, then what is the change you'll have? If it's an inverting amplifier, then the output should be, the phase will be shifting over. Okay, the phase of the signal will be shifting over and you'll have an increase in the amplitude. So the red one is for the inverting and the blue one is for the non-inverting output, amplifier output. Okay, so that's how the change in the signal is there. Okay, that will be a 180-degree phase shift. Okay, is that clear? So that's how the op-amp stuff is designed. Now we'll go to the next topic, the characteristics. The transfer characteristics for an inverting amplifier. I think we have already discussed. Ahatyan was telling. This was the characteristics for an inverting amplifier where the gain of K will be negative, right? So this is the saturation point for that particular op-amp. If it is a non-inverting, then the transition characteristics like this. Okay, this is V out by V in. We've already seen it. And then we'll go to some of the applications. Okay. That's the last topic for discussion today. Some applications like integrator, right? You know what's an integrator does? So you have a resistance with a capacitance. You have a integrator done with. Okay, it's exactly the opposite of a differentiator. Now, for differentiator, what will be the output? Circuit. In all these things, you have done it. So Hope and believe you understand it. For a differentiator, what would be the output? Integrator, you have a C and an R. For differentiator, Isaac,
So the resistor will be across
you're
output and
Isaac.
input.
I'll call you, wait. Isaac? Isaac Daniel, right? Yeah. Isaac? Not sure. Okay, take a guess, no problem. You have a resistor and a capacitor. Now for integrator, what would be the case? Now I'll jump to Isaac. Now you speak, Joy.
So V in and then a capacitor and then the resistor and it will go to the output, sir.
Let me see. Yeah, you're right. Okay, it's RC, right? Uh, I think this is the input. If the input is a square wave, okay, your output of your integrator would be a sawtooth, or a triangular wave, right? These are things I think you've already done with it. So I'm not going in detail. And last one is your summing amplifier. Okay. Summing amplifier includes you can have lot of input waveforms, V1, V2, V3, right? You add it and you get the output. Okay. So that's how uh, amplifier works with. So you have the input given to the non-inverting terminal. So it is V in into RF by whatever be the resistance. Okay, RG1. Similarly, V into equal to RF divided by RG2. Then RF V in 3 into RF divided by RG1. So forth. You can have any number of terms. Into reference voltage, this is coming under the inverting terminal. Okay, so the inverting terminal is, you know the value, 1 plus RF divided by, you have RG1, RG2, RG3, all in parallel. Okay, all in parallel coming into play. So that's how you calculate the output voltage. Okay. So it is sum of the inverting terminal and the voltage across the non-inverting terminal. So that gives you the output voltage for a summing amplifier. Is that clear? It's basically the thumb equation which we take into operation, right? This is the graph which you get across the output waveform. Okay. And some applications where we use OPAMP, we use it in low pass filter design, high pass filter design, band pass filter, and cascading. Right? So you know what is a low pass filter. What is a low pass filter? Mantino, Mantino, what is a low pass filter? Does Mantino, what is a low pass filter does? Yes, sir. Yes, Mantino. What does a low pass filter does? A low pass filter. Mantino, respond, man. What does a low pass filter does? You should have studied it. Not a very big. Antonio, what does a low pass filter does? Signal frequency. Signal frequency lower than cutoff. What does that mean? Signal frequency lower than cutoff frequency. Hey, Google says yes. Google Agatha, tell me. Only allows low frequency. Okay. Okay, and then yeah, it allows signals which are below a particular frequency called cutoff frequency. Okay, that is a low pass filter. High pass filter above the cutoff frequency. Band pass in between the two frequency band, between the lower and upper cutoff. Right. So this is an application where we use your op amps. Then we have strain gauge. And in strain gauge, this is the wheat bench arrangement. So based on the strain, the resistance value changes, and that's where you use your another application where you use your op-amp, right. This is how you estimate the strain gauge using half bridge. This is another application where we use your op-amps, right. The third application is PID controller. PID controller, all of you know what is PID, you should have learned about it in control systems. So, PID controllers also use op amps. Okay. This is the place they use this op amps. And this is the system block diagram. These are some of the applications of it. Okay. So, to sum up what we have seen for the day, we have seen about what is an op amp, what are the characteristics of an ideal op amp. Then we saw how an op amp, common op amp circuits are constructed, its characteristics, and then when we want to see some of the applications of op amp, right?